Okay, previously we were comparing population means using independent samples, and we had two different assumptions. The assumption that the variances were equal or the variances were not equal, because that made a difference how we computed our test statistic, whether we computed a pooled variance test statistic or a test statistic utilizing the pooled variance, or whether we kept the two individual variances and computed a degrees of freedom approximation. All right, so then the question when we adjourned last time was, how do you know? How do you know if the variances are equal or not? Well, if you can test hypotheses about population means, you can probably guess you could test population variances as well. And so that's what we're looking at first here. Okay, I believe most textbooks and lectures usually introduce the t-test first for the means comparisons because it's a t-score that you've already learned. And so to do this, we have to introduce a new test statistic. So if you're wondering why we didn't do this first, that's why I believe textbooks do it. Okay, here we're interested in answering examining research questions about two population variances. First, we're just listing the two-sided tests. We know that variance is measured in square units, and so therefore when we look at these normal distribution doesn't apply because we know we have this cutoff value at 0 for variances. We've already seen that in the test for a single population variance when we talked about chi-square. Okay, and so here we look at a test statistic that we call capital F. So this F statistic is simply the ratio of the two sample variances. Okay. In general, it doesn't matter which variance is numerator and which variance is denominator. Although we're going to make a little more, we're going to try to keep things a little more convenient as we go through to test this, and I'll explain that in just a minute. What does the F distribution look like? Well, if you're looking at my picture, it's going to look an awfully lot like what I draw for chi-square. All right, the lowest value is bounded below by 0, and it again is an asymmetric distribution. So that's what our F looks like. It is a probability distribution, therefore the area under the curve is 1. We're going to look up critical values in our textbook, and so they're going to be based on this right-hand area from our tables. It's going to call that P. We'll look at the table values in just a little bit, but let's set up the hypothesis testing scenario first. All right, so if we have this test of hypotheses comparing two variances, and we compute the ratio S1 squared over S2 squared. If H naught is true, what should this F value be? If H naught is true, that means that sigma 1 squared and sigma 2 squared are equal to each other. So therefore, if H naught is true, S1 squared and S2 squared should be close to each other, right? And if they're close to each other, then what should happen to F? Then F should be close to 1. Agreed? All right. F should be close to 1. Let's go ahead and write the explanation on there. Since S1 squared and S2 squared should be close to each other. Close to each other. That's kind of avoiding as much math speak as we can. Okay. What if it's false? Okay, so what's going to happen to this value for F? Okay, so if H naught is false, the value of F is going to get away from 1. It's going to tend to be what? Either close to 0 or bigger than 1, right? Okay, so we could break it into cases. So if H naught is false and, let's say, sigma 1 squared was greater than sigma 2 squared, then S1 squared in the numerator is going to tend to be bigger than S2 squared in the denominator. All right, so that would tell me that F would expect an F larger than 1, right? F would be larger than 1. All right, the second case here would be and sigma 1 squared is smaller than sigma 2 squared. And that would put our value of F. This is smaller than this. It's got to stay positive, though, so F would be close to 0. Critical values of the F distribution are found in Table A4 in your text. The F table goes across several pages, and if you change different textbooks or reference materials, the format of the F table can change. All right, so we'll discuss it as we see it in our Freund, Wilson, and Moore textbook. All right, the third edition here of the textbook, Table A4. Where this table starts, it says the F distribution with a value of P, that's right-hand area, equals 0.1. Okay? We have numerator degrees of freedom and denominator degrees of freedom. That's because our calculated value for F, we have these two variances. And remember from last time I said anytime you compute a variance measure, that variance has degrees of freedom. So that means there's two measures of degrees of freedom associated with this calculated F statistic. There's a measure of degrees of freedom associated with the numerator. There's a measure of degrees of freedom associated with the denominator. And the shape of the F distribution depends on those two degrees of freedom measures. So just like the T distribution and the chi-square distribution that change shape as degrees of freedom change, so does the F distribution, except it can change. If the numerator degrees of freedom stays the same and the denominator degrees of freedom changes, the F distribution still changes. Likewise, if the denominator degrees of freedom is held constant and the numerator degrees of freedom change, the F distribution changes shape. And therefore, the probabilities under the curve change in all those situations. All right, so we're looking for critical values, much like we did in the case of T and chi-square. We're looking at tail areas that tend to be small, right? And so for the F distribution, the smallest area, the largest p-value we can determine is 0.1 from the table. Okay? And so what we're looking at there, then our distribution, so if you drew this picture at the top of the table, that value of p they're talking about, this area over here is 0.1. Okay? That's what's going on here. Now read across the page. As you read across the page, you'll notice we have numerator degrees of freedom. They go from 1 and up through 10, 11, and then it continues on the next page, all right, across the top here. On the left-hand side, denominator degrees of freedom, 1, 2, 3 in increments of 1 till you get up to 30, and then it starts skipping like we saw with the chi-square and t tables, right? And if you look at adjacent numbers here, you'll see the changes of those are getting very, very small. So that's why you can see here going from, in this first column, going from 40 degrees of freedom to 45, the change in F is only 0.02. So filling it in isn't going to give you a lot more information. All right, so then as we want to change the right-hand area associated with a critical value, we're moving from page to page. So this is still P equals 0.1, and it goes over to numerator degrees of freedom of 120. You'll notice once we get up here to 15, 16, now it starts to jump. As we move across in a row, we're seeing little change there as well. Okay? And then it goes over to the next page, headed by 0.05. You have 2 pages for the right-hand area 0.05. You have 2 pages for right-hand area 0.025, 0.01. Also 2 pages 0.005, and then we're on to a different table. Okay, so the smallest right-hand area we can read off of the table is 0.005, or we would report smaller than 0.005. Okay, so now then, how do we go about looking at these tests here if we've got right-hand areas? Okay. All right, so note the following about the F distribution. We have 2 degrees of freedom measures are needed. Critical values of the F distribution are specified as follows in our textbook. The first value being uses P, that column header. That's right tail area or right-hand area. NDF denotes numerator degrees of freedom, and DDF denominator degrees of freedom. And they are always listed numerator first, denominator second. Now you could look at other reference material and it may put the right-hand area as a superscript, or it may put everything in parenthesis. All right, but when it comes to the 2 degrees of freedom measure, numerator is always listed first. Okay, so you may see a reference where it'll list the 2 degrees of freedom measures first, and then the area is the last thing. So you can usually, that's going to be the fractional value, okay? But whenever you look at the degrees of freedom, it's always numerator first. That's always consistent. Where the area is going is up to the author sometimes. All right, and again, you look at other references, and they may be looking at cumulative or left-hand area instead of right-hand area. So it's important to know what your reference is doing whenever you look at those tables. Okay. The right tail areas for the F distribution are given in our table. For values, right-hand areas that are 0.1 or smaller, we get those critical values. That doesn't read real well there, does it? Right tail areas for the F distribution are given. All right. For values, right tail areas, how about for right tail areas close to 1, we have the following relationship. All right. So suppose we saw this in our chi-square distribution. Remember we said values of F could be close to 0, but everything we looked up had right-hand areas that were very small. So if we have an F distribution, and so that if we wanted this left-hand area here, to be alpha over 2, started to write the F in the wrong place. If that left-hand area is alpha over 2, then that means then the right-hand area from this point on towards infinity is 1 minus alpha over 2. We would again need those values like 0.95, 0.99, etc. Okay, but this table clearly didn't have those, did it? All right. So we have this association here, an F that determines a right-hand area of 1 minus alpha over 2 for small values of alpha. And we identify its numerator degrees of freedom and denominator degrees of freedom, has the following association. You can look at 1 over an F with right-hand area alpha over 2. Switch the denominator and numerator degrees of freedom. So you look them up. So the denominator degrees of freedom goes from which value was in the denominator of the F you calculated. Okay, so that is switched. That's not a typographical error. Okay, so it says identify the numerator degrees of freedom for the application, and then you look at those are flipped, and we'll demonstrate that shortly. Okay. So we'll use this association when we look at some tests, since our table doesn't give us these kinds of values in the left side of the distribution. Again, like the chi-square distribution and like the t distribution, the shape of the F distribution changes as our numerator degrees of freedom and denominator degrees of freedom change. So we're still looking at, in all those cases, that we may have an F distribution here, and then it could get a little flatter. Some of them really flatten out as those values, degrees of freedom become larger. All right, so just an exercise in the looking at the table. Let's consider the following, where we have 7 numerator degrees of freedom and 10 denominator degrees of freedom, and look up those values here. So what we're looking at then is a fixed distribution for F, where 7 and 10 are don't change. So I want to look up the values associated with those right-hand areas. So if I go to the table, go to the page for point 1, go to the column for 7 numerator degrees of freedom, and go to the row for 10 denominator degrees of freedom, what value do you find? I have 2.41. Do you agree? Okay. Now notice, let's not turn the page yet. What happens is you stay in that same column and denominator degrees of freedom gets larger. So stay in the column for 7 and just scan down. Those critical values get smaller. All right. Now go back up to the row for 7 degrees of freedom for the for the 10 denominator degrees of freedom. Sorry, I misspeak there. Stay in the row for 10 denominator degrees of freedom and read across. All right, they change in that direction as well. So as numerator degrees of freedom increases, those values get smaller, probably not as rapidly as the ones we're seeing down the column. Okay, so we have 2.41 here, so that means that if I mark here 2.41, the right-hand area here is 0.1. All right, what's the next value? Go to the page for 0.05, column 7, row 10. At 3.14. .14 stays on the same curve, moves out a little farther, so the area to the right is 0.05. Go to the 0.025 page, column 7, the row headed by 10. That critical value is 3.95. And the area to the right of that, 0.025. The 0.01 page, column 7, row 10. .20, moving out a little farther. Supposed to be darker. Area to the right of that is we have 0.01. Get my leading 0 there. And lastly, 0.005, column 7, row 10 is 6.30. I think goes off the edge of my page here. So not to scale, but 6.30. And the area to the right of that is 0.005. Okay, so I bet you can see then how we're going to determine p-values, right? Instead, we're going to stay in the same row, same column, and go from page to page to find the two values between which our calculated F statistic falls. Okay? The F distribution is not symmetric in those degrees of freedom arguments, so we can't switch those. So we had the 0.1 right-hand area with 7 numerator degrees of freedom and 10 denominator degrees of freedom. That was equal to 2.41. What happens if you have those reversed? 10 numerator, 7 denominator degrees of freedom. That is a different distribution. So if you stay on the 0.1 page, column 10, row 7, differently than we did before, I have value 2.70. And then this one, the 0.05, 7, and 10, we already had that one as 3.14. Go to the next page. We won't go through all of them. We'll just do the next one. Column 10, row 7, for the right-hand area, 0.05, has a critical value of 3.64. All right, so what we said before was if the numerator degrees of freedom stays the same, and denominator degrees of freedom increases, the critical value of f decreases. If the denominator degrees of freedom stays the same, and numerator degrees of freedom increases, okay, well, we said they increase. Let's have a look here. Just stay on here. This is 0.05. So if you stay in the same row and go across, here the critical values of f increase here, then they begin to decrease in the next row. All right, so while we said earlier we were looking more down in here for low values of denominator degrees of freedom, they actually increase, don't they? So there isn't a uniform rule there, so we need to go back and correct the statement I made earlier, so we'll do that here in writing. Okay, so critical values of f can increase or decrease depending upon the denominator degrees of freedom we have for the. So I need to move my pre-printed information up, have a little more space to write. Some of the things to notice too, we kind of got the feel for with t, and we talked about this with the chi-square distribution. You know, those values of t around 2 or just a little bit larger, well, tended to be our critical values for 0.05. Here on the 0.05 table, notice how much these things change. So for very small denominator degrees of freedom, you can, and for one denominator degree of freedom, you can have a critical value that's in the hundreds. Okay, as you move down the column, it decreases rapidly within a column. Okay, but we don't have that kind of rule of thumb figure anymore about things about, you know, values around 2 like we did with the t distribution. All right, so now then let's talk about hypothesis tests. Okay, we can look at two-sided tests. We can look at right-sided tests. I didn't put the left-sided test here. And the reason I didn't put the left-sided test here was because our F table doesn't give left-sided values of F in the left side of the distribution. That's why it's not here. Does that mean I can't do a left-sided test? Well, I can. I just make it a right-sided test. If I arbitrarily assign 1 and 2 to establish a right-hand test, then can't I make sure that I establish which one's 1 and which one's 2 such that it's a right-hand test? So remember back in the two population tests we did for the mean, and I made the statement, if it's a right-hand test or a left-hand test is up to me. you know, when it was directional and which way I computed the difference. It's kind of the same thing here. If it's a right-hand test or a left-hand test, depends on which one I put in the numerator when I calculate. All right, so that's the same thing here. I want to set it up so it's right-hand so I don't have to do that 1 over business right here. Okay. So in both cases, we're looking at the same F statistic here. All right, two-sided test, two-sided rejection region. So if you're doing a two-sided test, I want to see that you compute this, all right, that you understand there's a left side to this, okay? Right side test, right side rejection region. And so here I called them N1 and N2 because 1 is in the numerator, 2 is in the denominator, so that's why the N1 is listed first here for numerator degrees of freedom. So for this application, I have 2 degrees of freedom. Numerator degrees of freedom is N1 minus 1. Denominator degrees of freedom is N2 minus 1. And so notice then the way these are set, 1 is always in the numerator, okay, with the index 1. Okay, I can choose to name whichever group in my study is 1. All right, we're based on random samples that are independent, and we have normal populations. All right. So let's just look at a generic test. Here I'm going to do a two-sided test for variance A and variance B. Are they equal or are they different? And I want to conduct those at the 0.05 level. I have sample A and sample B. Sample A based on 11 observations with a sample standard deviation of 12. B has 21 observations and a sample standard deviation of 23. You don't have to call them 1 and 2 always, remember. So I can track them. I'm going to call them sample size A, standard deviation A, sample size B, standard deviation B. Okay. So I want to be able to compute the test statistic. For now, I'm going to stick on the left side of this. I have divided it into columns for a reason here, so stay on the left side. So I'm going to compute my F statistic. That is going to be variance A over variance B. So that means I would have 12 squared divided by 23 squared. And when I compute this, I have a calculated test statistic of 0.2722. Rejection region. We have a two-sided test, so you do have to write a two-sided rejection region for me on this upcoming test and in the homework. All right, so reject the null hypothesis if. What happens? Let me put the rule back behind us here. All right, at the top of our screen, if the F value is small, smaller than what? And minimize the bleed through of the information behind. If F is small, if F is less than or equal to 1 over F determined by alpha over 2, alpha over 2 would be 0.025. All right, switch denominator degrees of freedom. As I set this up, B was in the denominator, so the denominator degrees of freedom for B is 20. Numerator degrees of freedom are 10. And so that would be if F is less than or equal to 1 over what value? Go to the table for 0.025. The column for 20, the row for 10. All right, so I have 1 over 3.42. Do you agree? Okay, and then that 3.42, when you compute that, reciprocal, I have 0.2924. So you'd reject if F were small. or in the right-hand side of the distribution. So you can think about the rejection regions. The rejection region is actually set up before you collect any data, right? If you know how big your samples are. I could write the rejection region before I ever computed the test statistic just by looking at the sample sizes, right? Or we'd reject if f is large. So if f is larger than f determined by right-hand area 0.025, this time stick with A's degrees of freedom in the numerator, which was 10, and 20 in the denominator. All right, so back on the first page of the 0.025 subtable, I have 2.77. Do you agree? And that matches this information here. So what's our decision? Populations A and B have the same or different variances. So on this side, if we were to draw our picture for our rejection region, we have 2.77 over here that determines this area 0.025. Over here, this area 0.025 is determined by 0.2924. And where we ended up is 0.2722. Agreed? So we would conclude that the two populations have different variance, right? Populations A and B have different variances. Alpha equals 0.05. Our calculated value of f, the calculated value we have has 10 numerator, 20 denominator degrees of freedom. Was 0.2722. And we have to be able to write a p-value. We'll get to that in just a little bit. Is everybody okay with what I did so far? Or you could have said, well, what would have happened if we would have put population B's information in the numerator and A in the denominator? We wouldn't necessarily do both. In fact, probably likely not. But I'm going to show you how what the differences between the two approaches are. So the other way we could have done this, so I guess at the top of this column, we could write a great big or. Test statistic is what? F is equal to the variance for sample B, divided by sample variance A. Wants to come out as population while I'm talking today. All right, so that would be 23 squared over 12 squared, or 23 divided by 12 and square the quotient. And when we do this, we have 3.6736. We didn't do it on the other side. Maybe that's what we should do here, is write numerator degrees of freedom here is equal to 20, and denominator degrees of freedom here is 10. So we could put the same NDF and DDF over here, and they would be in the reverse order, right? 10 and 20. That may help put the rest of that together. All right, so we reject the null hypothesis if f is smaller than what? 1 over an f determined by 0.025. Now, it's not going to be the same values over here because the numerator degrees of freedom and the denominator degrees of freedom are switched. Okay, so it can't be this one. All right, so it's going to be determined by an f with right-hand area 0.025, 10 numerator, 20 denominator degrees of freedom, that reciprocal. that information is over here because we've already looked it up once. It's this one. All right, so that's equal to 1 over 2.77, and that's 0.3610. All right, so the left side of the left-hand area associated with 0.3610 is 0.025. It's not the same value because it's not the same distribution. Okay, or you'd reject if f were larger than what? F determined by right-hand area 0.025, numerator degrees of freedom 20, denominator degrees of freedom 10. That's 3.42. We did look that one up. It's the denominator over here. So on the purple side over here, while my picture may look a lot the same for F, this right-hand area 0.025 is determined by 3.42. This left-hand area 0.025 is determined by 0.3610. Our calculated value for F is 3.67. It's out here. You'd have the same conclusion as we do on the left or red side. The populations A and B have different variances. We'd cite the same alpha. All right, so we'd have the same conclusion. Alpha equals 0.05. Our calculated value for F with 20 and 10 degrees of freedom is 3.6736. What would our p-value be? The p-value is going to be the probability that an F with 20 numerator and 10 denominator degrees of freedom is greater than or equal to 3.6736, and then multiply that probability by 2. Right? So we could say our p-value is 2 times the probability of F with 20 numerator, 10 denominator degrees of freedom being greater than or equal to 3.6736. All right, so we look up 3.6736 on our tables. I know it's in the right side of the distribution. It's bigger than 1. Okay, for this application, where it says we're bigger than 1, we're in the right side. We can use the right side. Okay. So 3.67. Now what you do is you go page by page through the F table. So we know we fell within the rejection region, so at 0.05 we will compare 3.67 to the values in column 20, row 10, from subtable to subtable. And then find the two values between which 3.6736 falls to determine our p-value. All right, so that we're actually, when we find that probability, it's only 1/2 of the p-value. So 1/2 p is between what two values? When you go to the 0.01 table, the critical value associated with 20 numerator and 10 denominator degrees of freedom is 4.41, right? The one for 0.025 here was 3.42, so that means the right-hand area is something between 0.01 and 0.025. Agreed? So this would be 0.01 and 0.025. And so our p-value then is twice this, 0.02, less than p less than 0.05. If we reject the null hypothesis, we have to compute a p-value that's less than alpha. Okay, and we have alpha was 0.05. So what would the p-value over here be? Well, it's this same p-value here. How do you find it? You have to go through all the column 10, row 20 entries and take the reciprocals of all of them, and then figure it out. That's why we set it up as a right-hand test. Okay? So you can get it from this. You just have to take the, whenever you went from subtable to subtable, from numerator degrees of freedom, denominator degrees of freedom, stay in those identifiers or locations across from one subtable to the next. You have to take the reciprocals of each of those over here. So why did I show this both ways? Okay, you can do it either way. Getting the p-value over here is not quite as straightforward as setting the test up such that the larger variance is in the numerator, but it can be done. All right. What happens? What happens is people tend to compute this, but look this up. Get the wrong rejection region with it. Or compute this and only the right-hand side. They said, oh, we don't have to do a two-sided test. It's only a right-side test, so we only look up the right-side rejection region. Well, if you set this up, you didn't reject it when, in fact, you should have. Right? Okay? Or you're comparing it to the wrong values over here. So logically, these two things are equivalent, provided you do all the steps that go together here in the left in red, or all the steps that go to logically fit together over here on the right that's done in purple. It doesn't matter which one you do. You don't have to do both, and I don't expect you to do both. You don't want to do both. Okay? You're not going to have that kind of time during a test. For homework, if you wanted to make sure you understand it, that's probably a good idea that you draw it out, because some of the cases, you're going to be out here in the middle and you don't reject, and you're not going to have a problem until you get to this kind of an illustration here, where you would reject on the left-hand side, but if you forget to check that critical value, you're going to miss it. Okay? Question?
On the left-hand side, you have it that we reject. On the right-hand, we don't reject.
We did. I didn't write it out as our conclusion's exactly the same when I said here. So here they are different. So we'd have the same conclusion right here, that statement, and our p-value is small. So if we were here, we'd get that same p-value over here. So it doesn't matter which way I do it. Just in the interest of space, I left too big a gap here. I didn't get it written in. So do understand that this is populations A and B are different. Maybe you left more space than I did. I wanted to write the probability statement, so that's why I didn't write it out again. Okay? Like we did on previous test statistics, we went through an exercise in computing p-values. Okay, so we'll try that again here and make sure we're clear with it. All right? Find the observed significance levels. And so when we write these, assume here that the index 1 is in the numerator. Okay? So whenever I write N1 and N2, assume that index 1 is what generated the F value 2.81. All right? So what do we have here? Two-sided test. We need to look up the areas here. So at F of 2.81, we're definitely in the right side of the distribution. Okay? And so that magnifying a right-hand side of an F distribution, what are our numerator degrees of freedom? 15. Denominator degrees of freedom, 17. All right. Now going from page to page or subtable to subtable, staying in column 15, row 17, find the two values between which the calculated value 2.81 falls. You should find value 2.72 that determines the right-hand area of what? 0.025. Then you should find a value 3.31 that determines the right-hand area of 0.01. Agreed? Our 2.81 is in here. So our p-value is 2 times the probability of an f with 15 numerator and 17 denominator degrees of freedom being greater than or equal to 2.81. So when we look up that area, we're finding half of the p-value. That probability is bounded below by 0.01 and above by 0.025. Double it, so this reads as p. So our p-value is between 0.02 and 0.05. Agreed? For our right-hand test, F is calculated at 7.62. We have sample size 14 and sample size 10. So for this application, our degrees of freedom are 13 and 9. The application of comparing two variances. Okay. We're going to do right-hand test only. So our p-value is not multiplied by 2, but is the probability of an f value with 13 numerator degrees of freedom, 9 denominator degrees of freedom, being greater than or equal to 7.62. All right, so go page to page, column 13, row 9. Now you could write all the values in there and draw them all in if you wish, but what we have is 6.15 is the largest value you can find, correct? And it determines the right-hand area of what? 0.005. So that means the best we can tell is that our p-value is what? Bigger or smaller? 7.62 is over here. So the area to the right of this is smaller than 0.005. So from your table in this textbook, p less than 0.005 is the best we can do. Okay? So if you write something else that might be true, but from your textbook you can't confirm that. Right-hand test, F is 3.21. Our two sample sizes are 8 and 7. So our p-value is not going to be doubled since it's right-hand test only. That's going to be the probability of an F with what degrees of freedom? 7 and 6, in that order, yes. Probability of F with 7 numerator and 6 denominator degrees of freedom being greater than or equal to 3.21. All right, so again, look at the tail of the distribution with F. It's 7 numerator, 6 denominator degrees of freedom. So work page to page. So what we have here is what? .01, determining a right-hand area of what? 0.1. And the next value is 4.21, determining a right-hand area of 0.05. And we are in there. All right, it's a right side test. We're not doubling anything. Okay, so that our p-value is smaller than 0.1, but larger than 0.05. And if you have to draw the picture to get it's right for F or for any of the test statistics, go ahead and draw the picture. I'd rather have you draw the picture and get it right than think you don't need the picture and miss it. Now, in either of these two cases here, if they were two-sided tests, we would double it. So up here, if it were a two-sided test and we were this extreme, you'd report p less than 0.01. Okay, it could be so extreme that 0.005 is maybe accurate, but we can't tell that. Okay, so if it's a two-sided test, make sure and double this so that it would be less than 0.01. If this were a two-sided test, it would be between 0.1 and 0.2. All right, now we have a two-sided test. We calculated an F value of 1.24, and we have our degrees of freedom, our sample sizes of 15 and 12 respectively. Okay, so that tells me my p-value is going to be 2 times something because it's two-sided, 2 times the probability of a calculated F with 14 numerator degrees of freedom and 11 denominator degrees of freedom. Probability of that is greater than or equal to positive 1.24. That's what I need to look up. So go to the row for 11 degrees of freedom, columns for 14, to find the two values between which the calculated value 1.24 falls. when you start going in this, your very first lookup, you get 2.18, determining a right-hand area of 0.10. Agreed? 1.24, we're over here. So kind of like what we talked about on the T-table, we fell off of the left-hand side of the table. That's kind of the analogous thing here. Okay? So the best I can do here is what? That the probability associated with 1.24, the right-hand probability, is bigger than 0.1. Okay? For the p-value, it would be twice that, greater than 0.2. So 1/2 p over 2 is equal to this quantity, so 1/2 p we know is bigger than 0.10, so that means our p-value is greater than 0.2, and that's the best we can tell. Now, if you wanted to put a upper bound on that of 1, that's fine, but not needed. So, or you could write 0.2 less than p less than 1. That's all we can tell. We know less than 1 because it's a probability distribution. If it were a one-sided test, you would just report p greater than 0.1. All right, so here I drew out the whole distribution so because we were so extreme here. It wasn't necessary to get all the finer graduations down here because we were so close to 1. Any questions on how to compute significance levels, observed significance levels? Last time we had looked at PROC-T tests for determining the differences between two population means under the assumptions of normality and then whether the population variances were equal or not equal to each other. So now how do we know which one we have? Which condition? We're going to test that. All right, so what we had before, this is the output from the previous SAS handout. All right, we identified our sample sizes N1 and N2. We've got that information here. 2.17, here is our Y bars, so here's our Y1 bar and our Y2 bar. The observed difference between them, and it's negative, so it's Y1 bar minus Y2 bar. Pardon? No, it's an arrow. Let's see, our standard deviations, we could look at S1 and S2. Okay. Here's our confidence interval for mu1. Here's our confidence interval for mu2. This is our confidence interval for mu1 minus mu2, assuming we're using S sub p squared. It's reasonable to do that. And then this 0.3641, that would be S sub p. It says standard deviation. The difference, Satterthwaite, here again we have a confidence interval for mu1 minus mu2. Notice the differences are the same. That's Y1 bar minus Y2 bars where the interval is centered at. The size of the interval is determined by the variance. These are 99% intervals given here. And so this is Satterthwaite. That means it's using that degrees of freedom star method that it assumes sigma 1 squared is different from sigma 2 squared. For pooled, the assumption is that sigma 1 squared is equal to sigma 2 squared. Now when SAS prints this, it doesn't put that extra blank line in there. I put that in there so we could annotate it more comfortably today. So if you compare this back to what we looked at last time, you don't have as much room to write. Okay, now at this point, we don't know which of those is the right thing to do. You have a question? SP squared is the pooled variance. So this interval is based on using the pooled variance. That pooled variance isn't printed, but the pooled standard deviation is. Okay, this output continues for proc t-test. Here, this is the variance assumption, so pooled variance. So here it's giving me the t-test. So up here is being tested whether or not design 1 is equal to design 2 with respect to the means, or whether the means are for design 1 and design 2 are different. Remember, proc t-test has one-sided alternatives as well. We just looked at two-sided last time. Okay, and so we talked about the output here. This is 26 is that N1 plus N2 minus 2. 25.827 is DF star. Equality of variances. This last thing is what we've talked about today. All right, so this is testing the variance expression design 1 variance. Is it equal to design 2's variance versus the two-sided alternative, that they are different. Okay, so what's going on here? This folded F, what that means is that SAS went back, examined which sample variance was bigger and made sure and put that in the numerator. Okay, so that folded F just says we set this up to be a right side, so we're going to so it's a right side test. Okay, or so we're checking things in the right side of the distribution. Now, how do you know which one it picked for the numerator, and how do you know which one it picked for the denominator? Let's go back one page, the printed page 10. All right. So the bit of information we need, it isn't down here in the intervals. Let's go up one more table. Okay. So here we see the differences in the means where that came from. Our standard deviations. Design 1 has a larger standard deviation than design 2. So design 1 was put in the numerator for what's called folded F. This 14 numerator degrees of freedom is because it recognized that was bigger than this, and it used its sample size minus 1. Okay? And then the other one would have 12 degrees of freedom. So what we've been labeling them here is numerator degrees of freedom and denominator degrees of freedom. Of course, then the value of F is going to be the variances. So if we take 0.3751 and square it and divide it by 0.3508 squared, you'll get 1.14. Okay. Now the p-value then is right-hand area doubled, and that's the 0.8254. Certainly much more specific than we can calculate it from the F table. The best we could tell is greater than 0.2. All right, so now in practice what you do in practice is you first read this test, okay, to write your conclusion. So when we write our conclusions, and I think last time we wrote everything at were we at 0.01 or 0.05? We've got 99% confidence intervals on here, so we'll do a 0.01 test, right? 0.01. I didn't transfer that over from the other handout, the alpha. Okay, so what do we have here? Designs 1 and 2 do not have different variances. We've conducted our test at the 0.01 level. Our value for F with 14 numerator and 12 denominator degrees of freedom that we've calculated is 1.14, and its observed significance level is 0.8254. All right, so based on that, we can write next bit, what says the appropriate t-test to compare the means uses the equal variance condition. All right, so everything we've written here is based on that information we're reading in the first step.
How could you tell that the variances were different? What do you use for a threshold?
And so we can make this statement about the variances because our calculated value for F has a very large p-value.
Is the cutoff for a large p-value greater than 0.5?
You compare p-value to alpha. So if p is larger than alpha, then you do not reject. So we do not reject this. Okay. Then, based on this, the appropriate t-test to compare the means uses the equal variance condition. That means we want to come up here, select the equal variance condition, and then this one in here is the one that's appropriate to read. If we had concluded that the variances are different, then step 2 would be the second one in the first table. All right, so now then we can write the conclusion based on the second part. Then that says designs 1 and 2, do they differ or not differ? If alpha is 0.01, they do not differ. Agreed? In mean computing time. What did we look at? A t with 26 degrees of freedom equal to negative 2.48, and its observed significance level 0.0200. Now, if our alpha had been 0.01, what would we have concluded? Pardon me, 0.05. We did 0.01. If our alpha had been 0.05, what would we have concluded? Variances are still equal. We'd still use this equal variances assumption up here. At alpha equals 0.05, we'd say that the computing times are different. If they're different, one must be faster. Which one is faster? The mean for design 1 is lower than the mean for design 2 that we observe. So it would mean that, so then if they are different, then we would make the conclusion that design 1 is faster if we were a 0.05 alpha. All right? What you are doing here on a very small scale is what's expected of you when you write your research report. Okay? You're going to write up your reports. You may have something like a materials and methods section where you say, here's the test, here are the procedures we used. All tests of significance were done at the 0.01 level. All tests of significance were done at the 0.05 level, whatever appropriate for your discipline or your topic. Okay? Make your statement about alpha. Then you get into your results. And so what we've written here are sentences are just very, very small sentences, right? But that's the kind of thing then that you would write up in your results. Then it becomes your job to do the discussion, perform the discussion there. Why did they come? What happened? What inferences can you draw? Okay. So here we're just making a very small statement. In practice, that small statement's going to get much larger. It's going to be 2 or 3 statements or a sentence, going from a sentence here to a paragraph in your paper. You're going to tell your audience what level of alpha you used for all your tests. You're going to tell your audience what your observed significance level was. You're not going to tell your audience what alpha is in every sentence like I've done here. I know that's overkill. But for this course, we'll keep it. That way I know you know. Okay? So that's what you communicate in your papers. All right? So on a very small scale, I'm asking what's expected of you to do in your master's report or your PhD dissertation. You'd have to report your statistical findings. Now, most usually, you don't report your calculated F values or your calculated test statistics in general. But you do report alpha, like in the materials and methods. You report it once. Okay? You do report the p-values as you make a statement. We found this was different than this. P equals what? Okay, we found this one was better. P equals what? So if you've been reading the papers and keep seeing the repetition of P in your research articles, that's what they're telling you. You may not understand the statistical method they used to conduct that test at this time. You may not understand that, but now hopefully those levels of significance you're reading make sense. Okay, so when you look at that and they say P equals 0.03 and this is not significant, well, then if they're a 0.01, if they've declared 0.01 as their significance levels, why? If you're a 0.05 person, you would find that is different. So that's why you report that. It gives the strength of the significance. So that some people, such as in pharmaceutical studies, may look at p-values 0.001, which look for very strong results that you may not see in some of the other disciplines. So always report your significance levels. Not just that it's less than alpha, not just that it's bigger than alpha, but what was it? Okay? Extra sheet back here. I don't know if... in the computer output, what we didn't discuss last time, where there were 2 figures at the end. So there was this panel plot here, which gives us a histogram of design 1, and then this is the histogram for design 2. Now, how do I know which one's which? There's a little 1 right here and a little 2 right here. So they're put in order. Or so if I had character data, it'd be put in alphabetical order. Okay? And then design 1 and design 2 gives me these little box plot images here. So I can see design 1. If I do, it doesn't list significance on this, but if I come to the conclusion that they are different, I can see design 1 is shifted to the left in its mean to the mean of design 2. So remember, the vertical bar across the center of a box plot is the median, and then some other symbols used to denote the mean. All right, so the line across here is the median for that group. In this case, it's not. We've seen some before where it was a plus sign, so it's got a diamond here at the location of the mean. All right, and we can see at a glance the dispersion here. The blue curves are if we assume a normal distribution with those. The red curves gives us a different information that we've not covered in this course. Okay. The other thing we can look at with each of these, because you might go, well, given that histogram, that normality thing might be questionable. And so then the last graph you're given is a QQ plot. And so again, this was on the handout last time that we didn't discuss the the graphics. And so the line here at 45 degrees is a reference line. Your data, you want your data to coincide as much as possible or lie close to that line. The more severe the departure from normality, then you'll start seeing points pull away. So in the tails of this distribution, we're seeing some departure from normality, but mostly this one's looking pretty good. This one's kind of got a little bit of a trend going on in it. With small samples, it's real hard, I think, to come to a conclusion of a severe departure from normality. Okay. Again, up in the corner here, our reference numbers, design 1 and design 2. So those are because normality was one of our assumptions. So these are two tools that help illustrate that, as well as if we conclude a difference, this kind of illustrates which the locations of the means, as well as what the dispersion of the data are. So we can see that equal variance assumption. We're seeing similar ranges in the data. So that equal variance assumption isn't too surprising. When we found that it's true, that's not surprising when we look at these graphs, the box plots. So the choices then, whenever you're looking at SAS output, if you're looking at listing output, which is just text file, you're not going to get these graphics. If you're doing HTML output with the graphics enabled, you get, by default, SAS is producing some nice graphics that helps you verify assumptions. Your choice whether you choose to include those in a report. Most usually not if you're using them for a diagnostic purpose. Very often a graph can help in your discussion. All right, but there are some limitations as to how many graphs you can publish. So sometimes you may have a graph you're looking at as you write your discussion, but you don't choose to release the graph. So a good graphic is almost always a good idea. A good graphic is always a good idea. Bad graph, not so much. All right, but yeah. So if we can get graphs that help us sort through our thoughts and our conclusions, I think it's a good thing.